Who can go ahead and start reading for us? Allison, you want to read? Go ahead.
Which of the following scenarios can be represented by an exponential function? Select all that apply.
Okay. So remember, we've talked about this kind of at the beginning. We always want to look for keywords or key symbols or key types of numbers that tell us that we have exponential growth. So does anybody notice any keywords, key numbers, key anything?
After a certain amount of years.
Okay, after a certain amount of years. Does that tell me about exponential growth though?
No.
No, because after a certain amount of years can be linear as well. Could be linear, so that doesn't really help us out too much, but keep going, keep looking.
I think E shows exponential growth function.
Each? Like there?
No, the answer choice E.
Oh, E. Yeah, what's special about E?
Because it has percentage inside of it.
There it is. There's a big one. So I'm going to make a list. I want everybody to write this in their notebooks. Exponential growth. If you're reading a word problem, look for percentages. So there's one. Now let's keep looking and then we'll keep writing in our list as we go. So is there another word or another phrase or another type of number that we see? And this is select all, so we know there's going to be more than one answer. Good. Alyssa, can you say that on public? You've got the other one I was looking for. There it is. Doubling. What type of word is the word doubling? Or in other words, what operation does doubling tell me to do?
Multiplication.
Times 2.
Times, not times 2, be careful, because doubling is times
Adding the same number?
Yeah, times itself, yeah. So any sort of multiplication word. So I'm going to make a short list. So doubling, tripling, tripling, by a factor of, so the word factor, that's another multiplication word. So anything that's telling me to multiply is going to be exponential. And then, let's see. There's one more, and this one is not something we've gone over. So I brought this question up because there's something here that we haven't really talked about, and I want to make sure we understand it. There's another key word, and I want you guys to think about money. So if you're thinking about money, what's another word in here? Okay, so deposit, you're on the right track because deposit is what you put in on the first day. That's like your starting amount. But what happens after you deposit the money? What does it say? Alyssa's got it as, again, the word is interest, but specifically compound interest. So let me explain what compound interest is. Okay, compound interest is like, and I bet you've probably seen it, you just didn't know what it was. But when you put money in a bank or in any sort of like savings account, it grows over time. It grows over time. So the money is, you maybe, let's say, I don't know, you put $100 into a savings account. After a year, it's going to grow a little bit. They're going to add maybe a couple more dollars to your account. Another year passes by, they put a little bit more money in your account. And that's why savings accounts are really helpful, because you end up with more than what you started with. And that's what compound interest is. That just means that your money is growing. But do we see a similar word somewhere in here? Read them all again. We have compound interest.
Yes.
Yeah, and then we have simple interest. Okay? Simple interest is not exponential growth. And this is one of those things that's just kind of hard to understand, because you guys are 13, 14 years old, maybe 12, and you probably don't have a bank account, and you probably don't really know what this looks like in real life. But for the purposes of this test, maybe I'll have time to go over it at a later time. I would love to explain what this is so that you guys actually understand it, because it's important. Money is important, right? But since I don't really have the time to explain the difference between simple interest and compound interest, just remember, simple, because it's simple, it's not going to be exponential. The only one that is exponential is compound interest. So if you see a similar question on the test and they try to trip you up with it, just make sure you write it down in your notebook, have it down right now, so you remember, compound interest is exponential, but not simple interest. Okay, so that's just kind of a quick thing to remember. So in this case, the only ones that are exponential are C, D, and E. Okay, any questions on this one? Okay, cool. Remember, by the way, speed, the speed of a car or the speed of a truck or the speed of whatever, of a rocket ship, speed is slope. And slope is what type of function? Where do we see slope? Good, I'm seeing it in the chat. That's linear. So if you see the word speed, that's a linear function. That is not exponential either. All right, so moving right along. So word problems, we just look for those keywords. But then, you know, we've seen these before. We have, sometimes it's going to ask us which of them is exponential, and you have a table. So who can remind me, what is the strategy for this type of problem? How do I figure out if it's exponential? What do I do? I have all these numbers. How do I figure out whether it's exponential or maybe linear?
You divide.
Good, I'm gonna divide. Now, what exactly am I dividing? From where to where?
Starting from the bottom to the top.
Starting from the bottom, exactly, it's like that song. So to figure out if it's exponential, we're gonna divide from bottom up. So we go from the bottom up. So I'm gonna take the bottom number. This is where you have to have a calculator. You can't do this one without a calculator. go from the bottom, you divide by the next number up. So I'm going to be doing 19,144 divided by 18,233. And I got 1.0499. And I kind of mentioned this the last time we did this, but we really want to make sure you write as many decimal spots as possible. So, and then don't simplify it until later. Don't round until later. So for now, I'm just keeping it pretty long, 1.044499. Then I do the next two. 18,233 divided by 17,364. And I get 1.0500. And we're just going to keep going until we have all of those numbers. You want to do it all the way up. 17,364 divided by 16,538. I got 1.0499. Two more times. Here we go. 16,538 divided by 15,750. 1.0500. And then last one, 15,750 divided by 15,000, 1.05. So I went all the way from the bottom to the top. Just divide, 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 divide. Do I end up with a constant percent or a constant rate of growth? What do you guys think? Are these numbers close enough? Do they round to the same number?
Yes.
Yeah, they sure do, because 1.0499, all those nines make me round up, right? So I'm going to get 1.05, 1.05. This also rounds up to 1.05, 1.05. All the way up, I get 1.05. So at the end, I have a constant rate. I have a rate of growth. Okay. Any questions on how I got that number, how I did all that? Okay, so I know that painting A is exponential. Now I want you guys to try the same thing with painting B. So go ahead and take about 2 minutes and do exactly what we just did. Divide and write down the answer you get each time. Don't try to keep that in your head. Write it down. That way you can keep track and see if you get the same answer each time. Take about 30 more seconds and let me know what you get. Let me know if you end up with a constant rate of growth. All right. About 10 more seconds. All right, so based on what you got, go ahead and tell me right now, tell me in the chat, is painting B exponential or not? Let me know, let me know. I'm looking for at least 5 people to send me an answer so I can get a sense of what you guys think. Is painting B exponential, yes or no? Okay, good. I'm seeing some correct answers. Can I get 2 more people? 2 more responses in the chat. Is it exponential, yes or no? Okay. All right, there they are. Okay. So we're actually kind of split. I'm seeing some yeses and some nos. So let's take a look. Let's look at it together. Okay. Going from the bottom up, I'm going to just show you what I got when I divided. I got 1.0200. For the next 2 numbers, when I divided, I got 1.0199. Then I got 1.0199 again. Then I got 1.02, just it stopped there. And then for the last 2, I also got 1.02. So when you get all these numbers, once you have those numbers down in your notebook, what you always want to think is, do they all round to the same answer? Do they all round to the same number? And so you got to start thinking, okay, here's these right here. What is 1.0199 round to?
$1.02.
Yeah, this gives me 1.02 because the 9 tells me to round up. So instead of 1.01, I get 1.02. Same thing with the next one. I also get 1.02. And with the final one, same idea. The zero just tells me to keep that 2 as a 2. I'm not rounding up, I'm just leaving it as a 2. So I get 1.02 for all of them. They all round to 1.02. So what does that mean? Is it exponential? Yeah, yes it is. Yes it is, because you got the same exact answer. That's what you look for. If you have the same answer every single time, then you bet yourself it is exponential. And that number that you get constantly, that's the rate of growth. So for painting A, the rate of growth is 1.05. For painting B, the rate of growth is 1.02. So they are both growing exponentially. Now, which one is growing at a faster rate?
Painting A.
Painting A. Good. Painting A is growing slightly faster than painting B. Any questions on this one? Someone asked me in the chat, I just want to bring this is a good question. Do you always have to round? Yes, you do. Because the reason we got slightly different numbers, even though we didn't get perfectly 1.02, we were able to round, and then we figured out that they were all 1.02. The reason you don't get perfect numbers is because in real world scenarios like these, we all know the real world isn't perfect, so your numbers aren't always going to be exactly the same. But as long as they are 1 decimal place away from each other, so like in this case, you know, 1.0199 rounds up to 1.02. As long as when you round, they are the same, then you're good. So after you round, check to see if they're all the same. If they are, you're good to go. Any other questions? Okay, one last thing. Are these growing at a constant rate, or are they growing at a constant percent rate? Is it a constant rate or is it a constant percent rate? And I'm asking this because I know this test is gonna test you on that. Think about the definition of exponential functions. Some of y'all in the chat are going crazy. What do we know about exponential functions? Exponential functions grow at constant percent rate. That's the key word, because constant rate, what type of function is just constant rate? There it is, Alyssa got it, linear. Constant rate is linear, constant percent rate, exponential. Remember we wrote it down on the previous slide, right? Percentages are exponential. So that's always think, that's the key word. Percentages are what we're working with. So if you see a question on the test and it says constant rate, and then later down it says constant percent rate, please click on the one that says percent rate. Don't get that question wrong, because I already told you which one it's going to be. Any questions? Any other remaining questions? Okay. All right, so we've done word problem, we've done a table, now let's look at a graph. Can I get a volunteer to read what we're doing in this one? Who can read? Who can read? Allison, go ahead.
This is examine.
Mhm.
Examine.
Examine, yeah.
Examine of graphs of f(x) and g of x shown below. F of x is a linear function and g of x is an exponential function. The value of f of x and g of x is equal at x, which is 5. Which of the following statements are true?
All right. So first of all, it's telling us that we have two graphs. We have f of x and we have g of x. And it says, okay, it says f of x is linear. So which color is f of x, blue or red? Which one is linear? Let me know in the chat, which one is linear? Blue or red? What do we think?
F of x is the blue one.
Good, f of x is the blue one, because linear functions, it's all in the name. A linear function is a straight line. So that blue is a straight line that is linear. G of x is exponential, and we already know that exponential functions, they curve, right? They curve. Okay, and then it's telling me that f of x and g of x are equal at x equals 5. On a graph, what does it mean when two functions are equal? What do they do at that point?
It intersects.
Good, they intersect. Okay, now do we see that in this graph, or did it cut off just before that? Where is that intersection point? It's telling us that they are equal at x equals 5. Is that on my graph or somewhere outside of it?
Somewhere outside.
Yeah, it's somewhere outside. It happens maybe somewhere off, like over here. But you can kind of see, right? Do we kind of see how the blue graph is going to reach a point where it touches and intersects the red graph? They're both heading in that direction. So they're going to touch. And then what's going to happen after they touch, after they meet? Which one is going to win? Which one's going to be much greater?
The red one?
The red one, right? Let's think about what's going to happen at this point. We can't see it because it's somewhere off the chart. But the red one is going to keep going really, really high. It's going to get steeper and steeper and steeper. Meanwhile, the blue one, what's that one going to do? Does the linear graph ever get steeper?
No.
No. It's constant. Constant because it's linear. So it's going to keep going at the same rate. It's just going to keep on going forever. So now let's go ahead and look at these answer choices. We want to see which of the following statements is true. And remember, f of x is the linear function and g of x is the exponential function. Now, what does the word exceed mean? What does it mean to exceed?
Like continue?
Continue, but it's a little more specific than that. When you exceed at something, are you doing well or are you doing poorly?
You're doing well.
You're doing well, right? So on a graph, to exceed just means to be above. To be above. So on this graph, let's see. It's saying, okay, is this true or false? True or false? F of x never exceeds g of x. So look on the graph. Is there a point where the blue line is on top of the red line? Is there a point or is there an area or a section where blue is on top of red? Don't overthink it. Don't overthink it. Let me know in the chat. Is there a section of this graph where blue is on top? There we go.
After they intersect?
After they intersect? After they intersect, who's on top?
Direct. No, this intersecting right here.
Oh, the first one. Yeah. Because we got two intersections, right? So in this whole area, this whole section right here, f of x exceeds g of x. In other words, f of x is on top, okay? So would answer choice A be true?
No.
No, it's false. F of x does exceed g of x for a moment, just for a few seconds. Then it goes back to being underneath. Same thing with B. G of x never exceeds f of x? No, that's false, because g of x does exceed f of x after that intersection point and before the first intersection point. So now let's see between these two. F of x exceeds g of x for values of x that are greater than 5. So remember that they meet again at x equals 5. On this x-axis, that's the 5. So after that 5, from here onwards, who's on top?
G of X.
G of X is on top. G of X exceeds. And on the other side, or actually that's enough to answer this question. So between C and D, and D, which one would be correct?
D.
D. G of X exceeds F of X for values of X that are greater than 5. So this is basically saying, okay, after the 5, G of X will always be on top, which makes sense, right? Let's look at what's going on here. G of X shoots upward really, really fast. After a certain point, that exponential graph is going to be much, much larger than the linear graph. And this kind of brings me, do you guys remember when we first started this whole section, this whole unit, when we talked about your little side hustle of mowing people's lawns, and then, you know, what was his name? Elon Musk was offering you 2 different deals. So remember, one of them was exponential growth and the other one was linear growth. And at first, most of you fell for it. You guys all chose the linear growth because it seemed to be bigger. It appeared to be better. But you didn't realize until I showed you that over time, exponential functions will always go faster than linear functions. Sometimes you got to give it a lot of time. For us, for that example, it was like 25 days later. After 25 days, the exponential function was much, much greater. You ended up with like $10 million, right? So always remember this. Eventually, exponential growth is always going to be faster, steeper, and better than linear growth. So they always win. Exponential functions always win in the end. Any questions on this problem? Okay, going once? Everybody feel okay about this? I just want to make sure today's the day to ask questions. Okay. All right, so one more of these. Which function displays the fastest growth? And what did I just say? What type of function always goes the fastest?
Exponential.
Exponential. Always goes the fastest. So what this question is asking me is which of these is exponential? So I just want everybody to take a look at the numbers in front of you, and you're just going to see if you can figure out any patterns. So I'm going to give everyone about a minute to start noticing the patterns. And you just want to kind of go this way. So what's the pattern to go from one number to the next number?
Add 2.
Add 2, yeah. So for this one, it's +2. +2. Now do the same thing with g of x and h of x, and then d of x. And just start thinking about what the pattern is, and we'll go through it together. All right, so for g of x, so f of x we already determined it's adding by 2. Let me do that a little bit more neatly. +2, +2, +2, +2. How about g of x? What's happening here? Okay, good. So I'm seeing it's -3 and then what?
-1
-1. Then what?
+1 and then
Plus one.
+3.
Yeah, +1 and then +3. So we haven't learned about this type of function yet, but when you see a function that like it goes down and then it comes back up, just like this one. So we started at 9, went down to 6, went down to 5, and then it seems to go back up. It's going to kind of look like this. That's called a quadratic function. We haven't talked about those yet, but we will very soon, actually. So that's not going to be right. That's not exponential. What about C, h of x? Okay, good. I'm seeing +7. Then what?
+1,
Good, +1. Then
+1,
+1 again. And then
+7.
+7. Okay. That one's a little weird too, right? It kind of goes up kind of quickly, then kind of slowly, and then kind of quickly again. Oops. Something like this. So this one, actually, let me draw it better. That one kind of looks like this. And that one is called a cubic function, which you won't learn about until algebra 2. So again, not the right pattern we're looking for, not the right pattern. By the way, what was f of x? Does anyone want to identify what type of function that one was? It was +2, +2, +2. What was that?
Linear.
Yeah, linear. Okay. So finally, we come to the last one. Looks like this is going to be our answer, and it is, but what's the pattern?
Multiply by 2.
Multiply times 2, times 2, times 2, times 2. And remember what we've been saying from the beginning, exponential functions grow by multiplication. So this is exponential. So you always want to find the one that is multiplying. That's why we did in this problem, that's why we had to divide from the bottom to the top. Because when we divide from the bottom up, we're doing the opposite of multiplication, right? So the reason that we divide is because exponential functions grow with multiplication. So by dividing, we can figure out if it is exponential or if it's not exponential. Now in this case, we could have done that too, actually. What you could have done is go from this way. So 4 divided by 2 is 4. 2 divided, or not 4, it's 2, my bad, it's 2. 2 divided by 1 is 2. 1 divided by 0.5 is 2. And 0.5 divided by 0.25 is 2. So you could have done it that way as well. It's just that these numbers were pretty easy. So it's pretty easy to notice the pattern just by looking at them. So any questions on this one? What's the easiest way to determine between linear and exponential? Does anyone want to take that question? That's a very good question. So how do I tell the difference between something that's growing linearly versus exponentially?
With linear, you add and subtract, and with exponential, you multiply and divide.
You got it. You got it. That's exactly it. So you know how f of x, it was +2, +2, +2, +2? That's linear because it's adding. And then the last one was times 2, times 2, times 2, times 2. That's how we know it's multiplication. So it's exponential. Does that help?
Yes, a lot.
Good. Linear is adding and subtracting. Exponential is multiplying and dividing. Okay? Good question. Anything else? All right. All right, now we're kind of switching over to a different, so we've talked about what is exponential and what is not exponential. Now we're just gonna look at exponential functions and talk about them a little bit. So for this one, we're gonna describe the transformation and state the y-intercept. Okay, so there's two different things we're gonna do. And I'll start off with the first one so that we can remember how to do this. The transformation, when I say transformation, I just want to know, is it going up, down, and then how many units? So in example number 1, how do we know the type of transformation? Where do we look to see where it's going? Okay, so we're not sure. That's fine. It's right here. Up 8 units. That's it. That's all. It's very easy. Very, very easy. But a lot of people forget. So I just wanted to go over this. So this transformation is just going up 8 units. So then what's going to be the y-intercept?
Eight.
Don't fall for the trick.
11.
Nope. No, we're not going to
There's
add 3 plus
3.
8. Nope. So when I say up 8 units, I don't mean from the origin. Up 8 units from, where is the y-intercept of the parent function?
1.
1. So it's up 8 units from 1. So what's the y-intercept?
9.
9. 0, 9. So that's the trick. Now, another way to check that, and matter of fact, how can you always check, no matter what function you have, how do you check for the y-intercept? What do you do? What do you plug in? If I'm looking for the
Do you
y-intercept,
plug in 0?
do you plug in 0? What do you guys think? The y-intercept, what is the y-intercept on a graph? Look at the one we just got. We have 0, 9. So heck yeah, that's what you do. You plug in 0. This is my input, and that's my output. So if you're looking for the y-intercept, if the question is asking me, what is the y-intercept? Plug in a 0. Doesn't matter if you've got an exponential graph, a linear graph, a quadratic graph, a cubic graph, a logarithmic graph, a sine graph, a tangent graph, a cotangent graph. There are so many functions y'all don't even know about. And no matter what, if I ask you what is the y-intercept, you're going to plug in a 0. So let me show you how this works. With example number 1, if I plug in a 0, let me erase what I've got. If I plug in a 0, I get this. What's 3 to the power of 0?
1.
1. What's 1 plus 8?
9.
9. See how we got 9? We already knew it was 9, but now I've shown you how to get it. So one more time. This is up 8 units from the 1. And the y-intercept is 9. How is 3 to the power of 0, 1? Who can tell me the general rule? Why is this 1? What is 1,300,462 to the power of 0?
1.
What's negative 5,256 to the power of 0?
1.
0. No, it's 1. It's 1. It's 1.
What is 5,462.35826 to the power of 0?
1.
What is anything to the power of 0?
1.
1. It will always equal 1.
Yes, ma'am. Always. We went over that 3 weeks ago. We've been over it. Anything to the power of 0 is 1. So try number 2, number 3, and number 4. Now that we understand how to do these, it should be pretty easy. Tell me the transformation, and then tell me what the y-intercept is. Take about a minute. All right, number 2, what's the transformation?
Up 5.
Up 5, good. So what's my y-intercept?
6.
6. 0, 6. Okay, number 3, what's my transformation?
Down 2.
Down 2, good. So what's my y-intercept?
Is it negative 1?
Mm-hmm. Good, because it's down 2 from 1. So 1 minus 2 is negative 1. And number 4, what's the transformation?
Down 9.
Down 9. So what's my y-intercept?
Negative 8.
Negative 8. Good. Okay, take a look. Take a moment. See if there's any confusion. And let me know. Let me know in the chat. I'll give you guys about a minute to ask any questions you have.
Miss, so like whenever like there's a number and an x above it, you can always substitute the x for 0.
Yeah, you can substitute the x for anything you want. But if you're looking for the y-intercept, you're always going to want to plug in a 0.
Okay.
Okay. Okay, number 3. Someone wants me to explain number 3. Sure. So the transformation is just based on the number that's there. So since I have minus 2, that's down 2 units. Now I'm going to show you the long way how to get the y-intercept. If I plug in a 0, 2 to the power of 0 minus 2. What's 2 to the power of 0?
1.
And what's 1 minus 2?
Negative 1.
Negative 1. So that's how we got 0 comma negative 1. Any other questions?
Miss, you know how for number 1 you set up 8 units for 1? For number 3 is down 2 from 1.
From 1. Yeah, you're always measuring from the 1. Usually with linear functions back in the day, you would measure from the 0. But with exponential functions, we always measure from the 1. That's just the trickier thing to remember. Any other questions? Any final questions? Okay, cool. All right. So now that we've been talking about transformations, let's actually look at a transformation. So here we have f of x and g of x, and it's asking me which of these is going to describe g of x in terms of f of x. So before we look into the answers, let's actually just see what's going on. If I start, we always want to look at the y-intercept. You're always going to look there because there is where you can count carefully. If I start at f of x, where do I have to go to get to g of x?
Down 3 units.
Down 3 units. Good. Down 3 units. So I'm just going to look for an answer choice that shows me that I'm going down 3 units. So which 2 options look good right now?
C and D.
C and D. C and D look great. But between C and D, we just got to remember that the way function notation works, the way these types of problems work, is it's got to be outside of the parentheses. So in this case, this is telling me to go down 3 units. What is C telling me to do? C is not telling me to go down 3 units. Where is it telling me to go? Anyone? Anyone remember? We've been over this before. We've learned it.
Is it left?
It's not left.
Is right.
It's right. Yeah. If it's inside the parentheses, it's telling me to go to the right. And then if it were adding, it would be left. Now, we've been over this before. We talked about this back in the day with linear functions. It's not going away. In fact, it's making a big comeback pretty soon. Not in this test, but the next chapter y'all learn about. So this is just something that we just always got to keep in mind. Okay, these function notation, they're just telling me where to go. So answer choice D is telling me to go down 3 units. C is telling me to go to the right. So that's not right. Oh, I didn't spell that right. Right, 3 units. B was telling me to go down 3 units. And A is something that we'll talk about later. We don't have to go over that right now. Any questions on this one? Take a moment, make sure you understand. All right. All right, here's another one, very similar. But this time, we're kind of putting 2 things together. So which of the following is the equation that represents the graph shown below. Take a look at your options. And start thinking about what might be the answer. In fact, I think I'm going to make this one a poll. I just want to see how we all feel about this. Go ahead and enter your answer into the poll. If you're not sure, if you just don't know, make your best guess. Rather than leaving it blank, I just want you to make your best guess, because I'd rather see a bunch of wrong answers than a bunch of empty answers. Because wrong answers help me to teach better, empty answers don't tell me anything. All right, take about 30 more seconds. I have 10 answers in so far. I would love to get at least 5 more. We have 18 students here today. Okay, 5, 4, 3, 2, and 1. Here's our results. All right, so actually, this is good. This is great. D was the most popular answer, and D is definitely correct. Now, a lot of people chose a couple other options, so let's just go over it really quickly. In fact, let me have someone else take over. Those of you who chose D, if anyone would like to explain how they came about that answer. How can you figure this one out?
The parent function have a y-intercept as 1.
Mm-hmm.
And if you go down 3, your y-intercept is -2.
Good. Perfect. So one way to think about it is, okay, this is telling me to go down 3 units. So physically, if I move it down 3 units from 1, I arrive at the correct place. So one way to think about it is visually, okay? What happens visually on the graph? That's good. Did anyone do it a different way? I see Guillermo says he just did the math. So what exactly does it mean to do the math? Now you're not so sure, huh? But remember what we did 2 slides ago. What can I always plug into each of these answers, each of these options?
The 0.
Yeah. If you plug in a 0, you'll see where the y-intercept is. Now, I know that the y-intercept is at -2. I know that this is where it should be, so now I can check each answer choice and see if that's what I get. Here, if I plug in a 0, 2 to the power of 0 is 1, so it's not A. Here, 2 to the power of 0 minus 3, that's 2 to the power of -2. 2 to the power of -2, what do I get? Wait, this is -3, not -2. What's 2 to the power of -3? What happens to an exponent when it's a negative number?
It turns into a fraction.
It's a fraction. Good. This would be 1 over 2 to the power of 3, which is 1/8. Okay, so it's not that. C, plug in a 0, I get 2 to the power of 0 plus 3, so that's 1 plus 3, which is 4. So it's not that. And then finally, 2 to the power of 0 minus 3, that's 1 minus 3, which is -2, and that's what I was looking for. So long story short, you can do it visually by just moving the imaginary parent function down 3 units, because we know it starts at 1, and if it goes down 3 units, there you go. Or mathematically. Mathematically works as well. Any questions on this one? Okay. Breezing right along. I want to get to as many as possible. We got 15 minutes left. Okay, back to tables. Back to tables. The table below represents the number of bacteria cells found in a petri dish in a science lab. Answer the following questions. So let's take a look at our table. We are looking at the number of days and the number of cells. So first one should be pretty easy. What is the starting amount of bacteria?
243.
Yeah, 243. 243. You could even say 243 cells. And then it's asking me, what is the rate of growth? So who can remind me, to find the rate of growth, what's the strategy? We've done it already today.
Divide.
Mm-hmm.
From the
Divide.
bottom.
Yeah, go from the bottom up. Divide, divide, divide. So let's go ahead and do that. 7776 divided by 3,888. What do I get?
2.
2.
2, yeah. And if I do it again, do I get the same answer?
2 again.
2 again.
Yes.
Yes.
Yeah, and you'll just keep getting 2 all the way up. So this one's actually pretty easy. You don't get any crazy decimals or anything like that. And so right off the bat, we always get 2 each time. So the rate of growth is 2. That's it. No rounding. In this example, it's pretty simple. So if that's my rate of growth, and my starting amount was 243, now we're going to write a function equation that represents the bacterial growth. So let me quickly go over how to do that. Remember that, oh yeah, it's going to be f of x equals a times b to the power of x. What does a represent?
The
What's A?
starting amount.
Starting amount. And b is the?
The growth rate.
Yep. Growth rate. Pretty easy. We're just going to put those two numbers together. So who can write my equation? What's it going to be?
F of x equals 243 minus 2 to the power of x.
Good, except we're not minusing. What's that?
Multiplied by.
Multiplying, yeah. Times 2 to the power of x. That is that. That is it. Exponential functions, you guys. Back in the day when we did linear functions and we had to find the slope, and then we had to figure out where the y-intercept was, and then we had to put it all together, y equals mx plus b. That was a lot harder. This is not that hard. This is a much quicker and easier process. So let's make sure we understand this, because at the end of the day, if this comes up on a test, that can potentially be a pretty easy question. Samantha's like, oh, y equals mx plus b is easy for me. You're special, Samantha. Most people do not like linear functions. So this is is not too bad, okay? You find the rate of growth by dividing. You find the starting amount just by looking at the table. You just look, just use your eyes. Where does it start? Where is it when it's 0? And now you just put those numbers together. Any questions? Questions on this? Okay, awesome. Well, now let's look at how we can do the same exact thing, but this time using a graph. So now the graph below represents the growth of a type of bacteria called NZ17. Answer the questions below. Same 3 questions. We're going to figure out what's the starting amount, figure out the rate, and then write the function. But it's a little bit harder because on a graph, you don't really see the numbers. You have to find the numbers yourself. So approximately, what is the starting amount of bacteria?
Like 77 or 78.
Like 77 or 78. Yeah, it's maybe a little bit above halfway between 70 and 80. So I like 78. I think 78 is a good guess, a good estimate.
What about that line right there? That zigzag?
Oh, good question. On a graph, when you have a zigzaggy thing like that, that just means that they skipped, because notice how they went straight to 70 and then from there it went up by tens. So that's just indicating that they basically cut out anything from 0 to 70. Does that make sense?
Yes.
Because otherwise, if they didn't do that, then this graph would be really, 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 really long, and then it wouldn't even start until like over here. So it's just a way to like make the graph a little bit shorter, because that's kind of a waste of space. Okay. Well, now, okay, we have the starting amount. That's not too bad. Now we have to find the rate of growth. And so in order to do that, the best way to do that is to turn your graph into a table. Because we know how to do tables. Tables we feel good about. We're just going to divide, divide, divide. So we're going to take the information from this graph and we're just going to stick it onto a table. I already know that it starts at 78, so 0 and 78. And now we're just going to go and see where is this at 1 and where is it at 2. So how many bacteria are there after 1 hour?
100.
Yep, 100. And what about after 2 hours?
135.
Approximately, yeah. Approximately 135. And that's all you need, because now you have a couple of numbers to work from, and now we can implement the same exact strategy. We're just going to divide from the bottom up. So go ahead and try that. What do we get the first time around?
1.35.
1.35. And what do you get the second time around?
1.282.
1.282. Now, we don't get the same answer because the numbers were not exact. I don't know if that's exactly 78. I don't know if that's exactly 135. So since we had to guess a little bit, the numbers, they're not going to be perfect. But that's okay, because we're just finding the approximate rate of growth. So approximately, both of those, we can basically say this is maybe like 1.3. Right? Those two numbers both are pretty close to 1.3. So that's a good approximation. And that's what you got to do with a graph. Unless every point is a perfect point, it's kind of hard. You have to estimate it a little bit, and that's okay. I'm not asking for the exact answer. I'm just asking for the approximate answer. And so finally, we have all of our information. Who can tell me what the function equation is going to be?
$78
Mm-hmm. Then what? $78
1.3 times 1.3.
1.3. And where's the x
And
go?
then put x as the exponent.
As the exponent. Good. That's it. So same process basically with a graph. You just have to kind of turn your graph into a table first. And that's going to be much easier than just by looking at the graph. So does anyone have any questions on this one? Going once. How do you make the equation? Follow the rule. I'll put it here as well. It's always going to be a times b to the power of x. So we just use the starting value, the growth rate, and that's it. Anyone else? Any other questions? Okay, we got about 5 more minutes, so I just want to jump. I can skip this one. This one's not as important. Just want to jump to these last 2 questions. So now we're going to go the opposite way. So now I have an equation. Now I'm going to get information from the equation. So we're kind of working backwards. Always bacteria with these questions. We love bacteria. Scientists are studying a bacteria sample. The function f of x equals 245 times 1.12 to the power of x gives the number of bacteria in the sample at the end of x days. What is the starting amount of bacteria?
245.
245, good. So just like before, now we're just working backwards. This is the starting amount. And then let's think about, is this bacteria growing or decaying?
Growing.
Good. How can you always tell?
It's more than 1.
More than 1. So this is greater than 1. So it's growth. Okay. What is the rate of growth?
1.12.
Yep. 1.12.
No.
The rate is 1.12. What is the percent rate?
12%.
You got it. Quickly, how to do that one more time. You just think about what number did I just add to the number 1. So this is 1 plus 0.12, and 0.12 as a percentage
Is
is
12.
12%. Questions on this one? Not too bad. When it goes in, when you have all the information in front of you, it's pretty easy to pick everything out. We're just going to do one more. I have about 3 minutes. Very easy, very similar. But okay, let's look at it. The value of a car can be modeled by C of t equals 28,000 times 0.73 to the power of t. What is the starting value of the car?
28,000.
28,000. Is the car's value growing or decaying?
Decaying.
Good. This time it's less than 1. This is less than 1. So it's decaying. Okay. What is the rate of decay?
0.73.
0.73. And what is the percent rate of decay?
27%.
Good. How'd you get that?
You had to subtract.
Subtract. Good. So 1 minus 0.73 gives me, what did you get? 0.27.
27.
And 0.27, that's 27. Oops, 27%. Good job. See, that's like one of the most important things, one of the things that a lot of people trip up on. So I'm very glad you guys understood that. When it's decaying, you have to subtract that value from 1, and that's how you get your percentage. Okay, so any quick, and that's it. That was it. So any remaining questions in these last 2 minutes? Okay. All right. So over this weekend, y'all, please spend some time reviewing. Please spend some time studying, and make sure those of you who promised me you're going to do your homework, get it done. Do not forget. Okay, I don't want y'all failing my class just because you forgot to do your homework, especially when you're able to do it as many times as you want. So that's an opportunity for you guys to do that for yourself. Get it done, bring those grades up, have a great and happy weekend, and I'll see you all on Monday. Goodbye, everyone.
Bye, Ms. Lopez. Have a nice weekend.
Have a nice
Bye, Miss
weekend. Thank
Lopez.
you. Bye.